laptops, so I can try now. It worked. The mic was not working. If you want me, if it is clearer for you to hear me through the laptop, I can try. Just tell me which one would be better for you. Okay. If now it's okay, so I will continue from here. Now it's okay. Shall I continue from here?
It's fine. I have my headphones connected, so you shouldn't speak at all because I can hear myself twice.
Okay, so let me try for the last time. I will close. Now it's clear.
Oh yeah, it's okay. Not a lot.
It's better now.
It's okay. It doesn't matter.
Okay, but now I'm using actually the laptop. I'm not using the mic. Yeah, not using the PC and the mic. So it should be better.
I
Mm-hmm.
think the other
No,
mic is better.
I don't know what's happening. Okay. Okay, I will work from here and let's see what will happen. Okay. Okay. There. So let's start. We will review the non-steroidal anti-inflammatory drugs, right? Okay. Can you remember when we said that we have in our phospholipid bilayer, when it is injured, the phospholipase A2 enzyme works on it to release what's called the arachidonic acid. Oh, sorry, I didn't share the slides, right? Oh, okay. Can you see the slides now? Okay, great. So it's released here from the phospholipid bilayer by the action of phospholipase A2, the arachidonic acid. And then we have, actually we said we have three pathways or three enzymes which would act on the arachidonic acid. Two of them are the well-known and the third is not well-known. And the most well-known actually, which is the topic of the non-steroidal anti-inflammatory drugs, is the cyclooxygenase pathway, where arachidonic acid, we have COX-1 and COX-2 would act on it. Okay?
Yeah.
Okay, and when they act on it, we will find that they would release prostaglandins. First, something called prostaglandin G2, and then this prostaglandin G2 gives me prostaglandin H2, and this H2 is unstable. So it would rapidly breakdown and give me prostaglandin I2, E2, F2, and thromboxane.
This part I'm actually familiar with because I studied it a lot. The problem I have with is once it comes to the
The drug?
derivatives. Yeah.
Okay, so I can skip all of this, right? Move to the drugs.
Yeah.
Okay, great.
Even the COX difference, you can skip.
Okay, so I would start with the classes of the drugs,
Okay.
right?
Yeah.
Okay, great. So for the classes for the non-steroidal anti-inflammatory drugs, we have selective COX inhibitors and non-selective. The non-selective means they would act on COX-1 and COX-2. The selective would act on COX-2 only. Okay? When we inhibit the COX enzymes, this means that the arachidonic acid will not be able to produce the prostaglandins, thromboxane, and prostacyclins. And these prostaglandins are inflammatory mediators. So by this, the non-steroidal anti-inflammatory drugs will act as anti-inflammatory and actually antipyretic and analgesic. Let's move to the classes. Do you need me to repeat this or you no? Okay. So the first class, and you can write down on a piece of paper the whole classes. The first one we have the salicylates, and the salicylates we call it salicylic acid derivative. Okay, this is the structure of the salicylic acid. I have a benzene ring and I have a carboxylic acid group, and also to this carboxylic acid group, hydroxyl group, the OH. From this salicylic acid, we cannot take salicylic acid. It would cause high irritation. So we make acetylation to this OH to give me acetyl salicylic acid, which we call the aspirin. So the aspirin, the other name for it is acetyl salicylic acid. It's a salicylic acid, but we made acetylation to the OH. Okay?
Yeah.
Okay. So number one, the OH must be also to the carboxylic acid. If it is meta or para, activity would decrease. What does this salicylic acid actually do? It inhibits the COX irreversibly. Irreversibly means that the enzyme would remain blocked for a very long period of time.
Yeah, due to
Okay?
the ionic bond after it is hydrolyzed.
We will say exactly what will happen. Actually, this acetyl salicylic acid or this aspirin would take this acetyl group, its own acetyl group, and transfer it to serine amino acid within the active site. Let's look here. Can you see here?
Yeah.
Acetyl group would go to the serine amino acid inside the COX enzyme. So now the COX enzyme is being acetylated. Okay?
Yeah.
And here they form ion dipole bond between the carboxylic acid and the OH for the serine to allow this acetyl group to be transferred. Okay?
Mm.
Okay. The aspirin itself or the acetyl salicylic acid undergo very rapid hydrolysis. This is an ester, right? So it is rapidly hydrolyzed to give the salicylic acid. So it remains inside our body as an aspirin for 1 to 2 hours. However, due to its irreversible blockage to the COX enzyme, it has long-lasting action. Okay?
But the diflunisal is not irreversible.
No, the diflunisal is reversible. I will talk about. I just need to finish the acetyl, and I will tell you about the diflunisal.
Yeah.
Okay? Is it clear?
Yeah.
Okay. Another point for the aspirin that it inhibits the thromboxane. That's why it is antiplatelet. It acts as an antiplatelet. Okay?
Yeah.
Okay, great. So for now, for the acetyl salicylic acid, we have carboxylic acid group. And this carboxylic acid group, we have also to its position, the OH. And if you can remember, we said the presence of carboxylic acid group is highly essential. Acidic group is essential to undergo ionic interaction, right?
Yeah.
Okay. So what does the acetyl salicylic acid or the aspirin would do? It causes irreversible inhibition of COX. If you are asked how, it transfers the acetyl group to the serine amino acid within the enzyme, blocking the channel for a long duration of action. Okay?
Yeah.
Okay, great. Concerning the other drug that you are have in this drug, is in this class, sorry, the diflunisal. This is the structure of the diflunisal. Again, it's having salicylic acid ring. This is a salicylic acid ring. And here in the para position, I have 2,4-difluorophenyl group. Okay?
Yeah.
This is 1, 2, 3, 4. So that's why we call it 2,4. Having this ring, this 2,4-difluorophenyl increases its hydrophobicity. It becomes more hydrophobic, leading to longer duration of action and more potency. So when you are asked why the diflunisal is more potent due to having this extra part actually is able to undergo extra hydrophobic interaction with COX enzyme. And whenever we are having extra interaction, this means that we have more potency or more activity. Is it clear?
Yeah.
Okay, great.
And it's metabolized also by the.
Tell you the metabolism now for it. Yes, I will pass with you through all the slides, even your own slides. Okay,
Okay.
don't worry.
Yeah.
Okay,
Thank you.
you're welcome. So all of this we have already mentioned. Okay, aspirin irreversibly inhibits the COX by acetylation of the serine. We said it's rapidly hydrolyzed to salicylic acid. After 1 or 2 hours, you would not have aspirin inside your blood. Okay, but its anti-inflammatory action is lasting longer because it inhibits it for
Irreversible.
yes. Again, it inhibits the thromboxane E2, so it's used as antiplatelets for treatment of ischemic attacks and stroke. And the aspirin is having here, if you can remember from the metabolism, it will have after the OH, okay? Either on the COH or the OH of the salicylic acid after its hydrolysis, right?
Yeah.
OH would undergo phase 2 metabolism. If you can remember, for the phase 2 metabolism, we said that it can be conjugated to amino acid, something like the glycine. Okay? Okay, great. So, till now, I just need to, have I opened? Yes, it's here. The first class, if you want to write as bullets or points, as we said, the salicylates. And for the salicylates, we have here two drugs, the aspirin, the acetyl salicylic acid, and the diflunisal. Okay, this is the structure of the salicylic acid. If you are asked, we have here. I don't know if she would ask you for the name, but the name is very easy. Actually, benzene attached to COH is benzoic acid, right? And here hydroxyl group at position 2, so it is called 2-hydroxybenzoic acid.
Yes.
Acetyl group on the OH, this is acetyl salicylic acid, which we call it the aspirin. This we already mentioned it, how it irreversibly inhibits the COX. The salicylic acid, its metabolism, since we are having COH or OH, so the OH in the carboxylic or the hydroxyl can undergo phase 2 metabolism, either glucouronic acid conjugation, right?
Yeah.
So glucouronic acid can be attached to the COH or the OH, either here or here. Or it can be attached to glycine amino acid.
Okay.
Is it clear?
Yeah.
The aspirin itself would undergo ester hydrolysis to give salicylic acid, and then it can undergo one of these metabolites.
Okay.
The other three here is benzene or aromatic hydroxylation. We said the most common one is that we can cause para-hydroxylation, right?
Yeah.
Okay, so here it's telling you we can here para to the OH, we can add here OH, and the other not common, it can be also to the OH, so it can be here. Can you remember? It said para or ortho, but para is more happening because the static clash is less. But the ortho can happen also, or can happen in the ortho and the para at the same time, but this is a minor metabolite. Okay?
Yeah.
Okay, great. If anything is not clear, just stop me. Okay? I'm trying to study with you the slides, these slides.
Yeah. Yeah.
Okay. So actually, the therapeutic properties for any non-steroidal anti-inflammatory drugs, if you are asked, anti-inflammatory, analgesic, and antipyretic. Antipyretic means that it decreases the temperature if you are having fever. Another therapeutic property for the aspirin, since it's able to inhibit the thromboxane, so it is used as anti-aggregant.
Some of
Okay?
them have it, but just not as much because of the reversible
Yes,
mechanism.
the anti-aggregant is not a property for all the anti-inflammatory. The common between all of them is anti-inflammatory, antipyretic, and analgesic. Okay? Okay, great. Again, for the pharmacokinetic, we said that it's easily hydrolyzed by the esterase to give the salicylic acid, and the acetyl group is released as acetic acid. Okay?
Yeah.
Is it clear? Releasing the acetic acid is responsible for the vinegar smell for the degraded aspirin. If you have an aspirin which underwent degradation, you will find that it has a vinegar smell. Why? Because upon its degradation, it gives acetic acid. Okay?
Yeah.
Is it clear?
Yeah.
Okay, great. It has interaction with oral anticoagulants because the aspirin itself is an antiplatelet. So if you are taking with it other oral anticoagulants, you should be very precaution because not to cause side effects, not to cause bleeding.
Okay.
Okay? Okay, great.
So is the drug-drug interaction with other anticoagulants?
Yes, you should be very cautious when you are taking them together because both of them would cause antiplatelet aggregation, right? So if you increase the dose, you can have adverse effect by causing severe bleeding, and it can be fatal also.
Yeah.
Okay. The other drug in this class, the diphenhydramine, as we said, it causes reversible inhibition. This extra part undergo extra hydrophobic interaction with the COX. That's why it's more potent than the aspirin.
Yeah.
Okay?
Why do you
This
specifically
drug,
use aspirin?
yes, this drug actually is used in cases of rheumatoid arthritis and osteoarthritis. Okay?
Yeah.
Is it clear?
Yeah.
Okay, great. Do you have any problem with the first class?
Actually, no, but it's really nice to revise all the
Uh,
class.
the class, this class again?
No, no. This class, I find it the easier. This one and paracetamol. And
Okay,
I have more trouble with the Phenax, the Phenix, and
we will come
Odocin.
to it. I'm just for this part. Okay, right?
Yeah, yeah. Thank you so much.
Great, you're welcome, dear. So the other class, okay, let's go like, okay, the other class, it's telling about the aryl alkanoic acid derivatives, or what they would say about it, the aryl acetic acid or aryl propionic acid. Okay?
Yeah,
Actually, this class is having a general, like a general SAR, that we are having an aryl ring attached to carbon and then carboxylic acid group. Okay? So between the carboxylic acid group and the aryl, we do have one carbon spacer here. This is a one carbon spacer. Okay?
yeah,
This carbon can have the other two substituent hydrogens, or it can have another R group, another alkyl group. If the R here is not hydrogen, if it is having alkyl group, another aryl group or alkyl group, therefore this carbon at this time will be attached to four different groups, right?
yeah. So it would be chiral. Yeah,
R, COOH, and aromatic ring. So by this carbon will be a chiral center, right?
yeah,
Okay, the presence of another carbon here attached to this carbon spacer being chiral, so I would have R and S enantiomers. The active one is the S enantiomer, okay? And if we are having here a CH3, by this we are gonna have three carbons. This carbon, the first one, the second, and the third for the carboxylic acid. Having here three carbons, they would call it propionic acid. That's why they would call it aryl propionic acid derivatives.
okay.
Is it clear?
Yeah.
Okay,
So the
great.
acetic acid is only when it's the one CH, and then if there's the two spacers, it's
Yes, if we
propionic.
are having CH2COOH, it's gonna be aryl acetic acid.
Okay.
Okay,
Yeah.
is it clear till now?
Yes. Thank you.
Okay, so let's start with the first example here, the endomethacin. Now let's apply the SAR on the endomethacin. We are having here the CH2COOH, right?
Yeah.
So we are having here one carbon spacer and the carboxylic acid. This one carbon spacer should be attached to aromatic ring. Do we have an aromatic ring? Yes, this ring, we call it indole ring. That's why it's called endomethacin, because this ring here, the benzene ring attached to this five-membered ring having the nitrogen, it's called indole. Okay?
Yeah.
Is it clear?
Yeah.
Okay. So here, this part, they would say it indole acetic acid. Okay? And then we are having here CH3. And from this nitrogen, we have a carbonyl group attached to benzene ring. And in the para position, we are having a chlorine or a chloro group. Focus. This chlorobenzene, this second aromatic ring, will undergo interaction with a pocket or an area within the COX enzyme. Okay?
Yeah.
And again, this indole also undergo interaction with another pocket.
Okay.
This carboxylic acid, as we said, is essential in all non-steroidal anti-inflammatory drugs in order to be able to bind to the COX active site, right?
Yeah.
Okay. This CH3 with this group causes non-coplanarity. To be coplanar means to be in the same plane. Non-coplanar, not in the same plane. And we need actually these two parts to be in non-coplanarity, not to be in the same plane, to be able to bind to different pockets for the enzyme. So these two groups, the presence of the CH3 and the chlorobenzene causes or increases the non-coplanarity, increasing the activity of the drug. Okay? Okay. The endomethacin is highly bound to plasma protein and it's toxic for the GIT, as we said, causing the dual insult effect. Okay?
Yeah.
Is it clear?
Yeah.
Okay, we said that the carbon here, one carbon spacer, when they tried increasing the carbon spacer, they found that the activity decreased. That's why it's telling you here, carboxylic acid group is located one carbon away from the aromatic ring. Increasing this distance would decrease the activity.
Actually, it binds to the plasma membrane of the bladder of the hepatocytes.
Plasma protein like the albumin.
Ah, okay, albumin. Okay.
Albumin, yes. Okay. Is it clear?
Yeah.
Okay, great. Other drug you are having is the Solendic.
Yeah.
Let's apply the SAR also. We are having here aromatic ring. We are having one carbon spacer and COOH. So it is abiding the general SAR, right?
Yeah.
Again, it's having CH3, and here it's having C double bond C, and then this aromatic ring attached to this substituent.
Yeah. One
You
spacer
will,
and double bond.
yes, you will find also that this CH3 and this ring, the same as the endomethacin, would increase the non-coplanarity and it plays a role in the activity. But I have here a point in the cylindic. Is the cylindic having indole ring?
No.
No. Instead of the nitrogen, I'm having C double bond C here, right?
Yeah.
Okay, this ring is called indene ring. So the endomethacin is having indole acetic acid, and the cylindic is having indene acetic acid. Okay?
Yeah.
The presence of C double bond C, whenever you have C double bond C, you would have Z and E isomers. Can you remember the Z and E isomer from the organic courses?
Yeah.
Okay, the Z means when I draw here a line at the double bond, it means that the heavy groups are on the same side,
Yeah.
right?
Yeah.
If the heavy groups, like in this case, on opposite sides, it's called E isomer.
Yeah.
Okay? Okay, the form or the active form that's used for the cylandic is the Z isomer and not the E.
Active is Z. Okay.
Yes. Okay?
Yeah.
Is it clear to now? The Z isomer is more active.
Yeah.
Okay.
But
Actually,
it's not administered as a racemic mixture. It's just
it's given as a racemic mixture, but the Z isomer is active.
okay.
It's the active. Okay. Okay. This cylandic is less GIT toxic. Why? This would go to the coming slide. Actually, the cylandic in its shape like this, it's a prodrug. It's not active. It's activated after its metabolism. Okay?
Yeah.
So when it is given, it's not active in this form, so it will not cause the GIT dual effect, right? It will not decrease the prostaglandins at this part.
Yeah.
That's why I will come here. The cylindic is a prodrug. It's inactive. This form is inactive. It must be metabolized in order to be active, and this decreases the direct exposure of the gastric mucosa to the active drug. That's why it's less GIT toxic than the endomethacin.
Okay.
Okay?
Yeah.
What happens in the metabolism? We have mainly two metabolisms. Either this sulfur would undergo further S oxidation to give me the sulfone, okay? And this sulfone, it's inactive in the anti-inflammatory path. It has anti-tumor, and this is not our topic here. So they consider it for the anti-inflammatory property, it's inactive. Or this double bond O is removed. Reduction takes place to give me the sulfide. Okay?
yeah,
This sulfide metabolite is the one which is active, which gives me the anti-inflammatory effect.
okay,
Is it clear?
yeah,
Okay, great. For the endomethacin, its metabolism, let's see what would happen. Since we are having again COOH, so this COOH can undergo phase 2 metabolism, glucuronic acid conjugation, right?
yeah, of course, yeah,
Okay. This N C double bond O, it's an amide, right?
yeah,
Amide can undergo amide hydrolysis by breaking the bond between the nitrogen and the carbonyl group. So this would become an H. Is it easy?
yeah,
Sure?
yeah,
Okay. Again, this nitrogen, sorry, this OCH3, oxygen and carbon, so we can break the bond between them and cause something called O demethylation or O dealkylation. Can you remember this?
yeah,
So it would become, instead of OCH3, OH. And then this metabolite can undergo further metabolism, amide hydrolysis. And then following the amide hydrolysis, we would move to glucuronic acid conjugation. So this pathway actually is combining these two with it. Okay? Is it clear?
yeah.
It's easy this. Do you have any problem in this part?
No, thank you.
Great. So till now, for the aryl acetic acid derivatives, we have the endomethacin. I'm repeating to give you time if you want to write as a summary for you.
Yeah,
We have the endomethacin and we have the silandic. The endomethacin is having indole acetic acid, one carbon spacer, COH, and the indole aromatic ring. Actually, the methyl group and the chlorobenzene increases its non-coplanarity. That's why it's active. We need it. The more the non-coplanarity, the more the potency of the drug or the activity of the drug. Okay?
yeah,
This endomethacin undergo several metabolic pathways, and all the metabolics are less active or inactive. Okay?
yeah,
For the Solendic, it's a pro-drug. It's not active. It should be activated by metabolism, by reduction to give me the sulfide, which is the one having the anti-inflammatory activity. Other metabolism which is common is S oxidation to give me the sulfone. This does not have any anti-inflammatory activity. The Z isomer is the more active form, and it's having indene acetic acid. Okay, not indole. Is it clear?
yeah.
Okay. Another example is the diclofenac. What is the diclofenac here? Again, it's aryl acetic acid. From where did I know? I have here aromatic ring, I have CH2 and carboxylic acid group. So it is the general star for the aryl acetic acid, right?
Yeah, but it has a spacer? No.
No, here one carbon spacer also CH.
Yeah, yeah,
Okay?
yeah,
Okay. From here we are having a nitrogen attached to dichlorobenzene ring. Okay? Again, these two dichloros are very important because they increase the non-coplanarity, increasing the potency. The same idea. Okay?
the cylinder is also not planar because of the Z and E conformation.
No, here the cylindic, the one that causes the non-coplanarity, actually the Z isomer to have the bulky groups on the same side, the presence of this CH3 and this ring increases the non-coplanarity also.
Okay, okay,
So here, if these two chloro groups are not present, so they will not be non-coplanar, and this would decrease the potency. So the presence of this ring is very important for the activity. Okay?
yeah,
Okay. The diclofenac actually is having three different mechanisms for acting as anti-inflammatory drug. Number one, it inhibits the COX enzyme, inhibiting the conversion of arachidonic acid to the prostaglandins and prostacyclins.
yeah,
Number two, it inhibits also the lipoxygenase pathway, not only the COX enzymes. Okay?
yeah,
Number three, it decreases the arachidonic acid release and increase its reuptake. So you have two different mechanisms of actions for the diclofenac. Okay, is it clear?
Yeah.
Okay. The metabolism of the diclofenac is very important. Whenever you are having an aromatic ring attached to a nitrogen, you will find that the metabolism will pass by para-hydroxylation, adding here OH because the NH is an electron donating group, so para-hydroxylation would take place. And then further oxidation takes place to this OH to give me C double bond O. Okay. This ring now, these two carbons having C double bond O, these two carbons are highly electrophilic. They are having high partial positive charge. This ring, we call it quinone-imine ring because C double bond N is imine. So this is called quinone-imine metabolite. This ring is highly toxic. Why? Because these two carbons, which are highly electrophilic, they can react very quickly with any nucleophile inside your body. And actually, your body is having many nucleophilic centers in the protein and your DNA, right?
Yeah.
So this actually metabolite is easily reacting with hepatic proteins inside the liver, causing hepatotoxicity. Okay, this SH means it's a cysteine. This is a part of the cysteine amino acid in proteins inside your liver. So if this electrophilic center was able to bind to proteins of the liver, this would cause toxicity to your liver. So that's why we call it, or we say that it causes hepatotoxicity, or it is hepatotoxic. Okay, inside your body, Allah gave us mechanism that causes spontaneous detoxification, which is the glutathione. The glutathione is already having a cysteine amino acid. So it can go very quickly and react with this electrophilic site instead of reacting with the hepatic proteins. That's why we say that it is a detoxification pathway. The problem would be if we took large amount from the diclofenac. So depletion would occur to the glutathione, right?
Yeah.
And when the glutathione is not there inside our body anymore, this drug or this metabolite would go and react with your liver proteins. That's why upon overdose, or if someone is trying to commit suicide by taking large amount from the diclofenac, we give something called the antidote. This antidote is having also SH group, which would go and react with this toxic metabolite instead of the hepatic protein.
Okay.
So for the diclofenac, I need you to come out with three arrows. The diclofenac, upon metabolism, it gives the quinone-imine metabolite, which is toxic.
Okay.
Actually, this quinone-imine bring from it three arrows. It's either gonna, this carbon will react with hepatic proteins, causing hepatotoxicity, or with glutathione, which is present naturally inside your body to cause the detoxification process, or we can give the third arrow antidote to react with this electrophilic carbon instead of our protein. I can remember it's found somewhere. I wrote it somewhere, the antidote. We will come for it. Okay?
Yeah,
Is
this
it
is
for
naloxone. No, sorry.
no?
Uh,
It's acetylcysteine, the antidote.
yeah, yeah.
Okay.
Yeah.
Is it clear till now?
Yeah.
Is it easier? You can follow with me?
Yeah.
Sure. Okay.
Yeah.
Antidote is acetylcysteine if you want to write it, but I'm sure I wrote it somewhere. Acetylcysteine, the third arrow, this acetylcysteine is an antidote. Actually, it will come and react here as the glutathione would do.
Okay.
Okay, is it clear?
Yeah.
Okay, great. Okay, by this, these are the two drugs mainly. Actually, we have more, but these are the most famous drugs for the aryl acetic acid.
Okay.
Now the aryl propionic acid, as we said, we will have this carbon having, this is the one of the aryl propionic acid. This carbon would have CH3 group, right?
Yeah.
Again, we are having aromatic ring, one carbon spacer, COH, but this carbon is going to have R group. By this carbon would be a chiral center. And we said chiral center, therefore we would have S and R, and we said that the S is the more active form. Okay? Is it clear?
Yeah.
Okay. Having this carbon actually increases the anti-inflammatory activity. This methyl group on the one carbon spacer increases the anti-inflammatory activity.
Okay.
Moving to the metabolism of the ibuprofen, it's very easy if you understood the metabolism slides. Can you remember we said that here is an alkyl chain, right?
Yeah.
This is an alkyl chain.
Yeah.
The carbon directly attached to benzene ring is called benzylic carbon, right?
Yeah.
So we have one type of metabolism called benzylic oxidation that we will come from this carbon and attach to it OH group.
Yeah.
Okay. For alkyl chain, we have omega oxidation, adding OH on the terminal carbon, or omega minus 1 oxidation, adding OH on this carbon, the one before the terminal. Right? Is it clear?
Yeah.
So this is the benzylic oxidation we are having here. This is omega minus 1, and this is omega oxidation.
Okay.
Here from omega oxidation, it became CH2OH, it's an alcohol. This alcohol can undergo further oxidation to give acid. Okay?
Yeah.
Is it clear?
Yeah.
Okay.
Wait, sorry. The red CH3, it increases.
Activity. The presence of the CH3. Yes. Okay. Another drug. Also, it is from the aryl propionic acid, the ketoprofen. From where do I know that it belongs to this class? Again, I'm having aromatic ring, CHCOH, and on this carbon, I'm having a methyl group. So it is aryl propionic acid. Okay. What is the metabolism mentioned in your slides? That this drug would undergo aromatic oxidation. In the para position, I will add here OH. Okay?
Yeah.
This is one type oxidation or reduction. This is a ketone. Ketone, when it undergo reduction, it give me alcohol.
Okay.
Other example is the phenoprofen. Again, it's aryl propionic acid, aromatic ring carbon COH and CH3 on the carbon. The same as the ketoprofen. What type of metabolism will take place? Here, only oxidation will take place. No reduction because we don't have a ketone here. It's an ether.
Okay.
Okay? Is it clear?
Yeah.
Okay, great. So let's go back to your slides. Here we have the aryl or heteroaryl acetic acid derivatives. We have here different examples. The endomethacin, the first one. We already mentioned the metabolism. You don't need me to repeat again, right?
It's good. Thank you.
Okay, we said it's highly bound to the plasma protein, cause GIT side effects, and uses in cases of inflammatory diseases. This is the solandic. It's having the indene ring. We said we have the Z. From where do I know that this Z? Draw a line here at the C double bond C. The two bulky groups on the same direction. It's Z. They are on the opposite directions here, so it is E.
Yeah.
Okay. The solandic itself is inactive. It's a prodrug. It has an active metabolite, which is the sulfide. After removing the double bond O, this is the active metabolite. Another famous metabolite is the sulfone, okay? And it's telling you that, again, this COH can undergo glucuronic acid conjugation, okay?
Yeah.
Is it clear?
Yeah.
It's written here, Salandic is a prodrug and it's having less GIT toxicity. Okay. For the diclofenac, I told you it has three mechanisms of action: inhibiting COX, inhibiting lipoxygenase, inhibiting release of arachidonic acid, and stimulating its reuptake. It's more active than the endomethacin. Okay, is it clear? Do you get what I'm saying? Okay. We said here the metabolism for it. One type I will come. This is easy part for the metabolism. What?
I think I showed you.
Sorry.
Go one more slide up.
Here it's given in the form of a salt.
Ah, okay. Yeah, yeah. So it can.
Yes, you can
Yeah.
give it in the form of salt. Yes, this is would be having the COH would lose the proton to be CO minus, and the sodium having a positive. So this is a salt form of the diclofenac.
Yeah. The anyways the COH makes an ionic bond, so it doesn't matter if it's Na
Yeah,
or.
inside your body, it will undergo ionic bond, no problem.
Yeah.
Okay.
Yeah.
Yes, here we mentioned the hepatotoxicity part. Do you have any problem with it?
No.
Okay. Other metabolic pathways for the diclofenac. We said the first part here that parahydroxylation would take place, and then this actually is the major one, which would give the quinolamine that causes hepatotoxicity.
Okay.
Okay.
Yeah.
Other pathways that can take place, but actually they are minor, they are not the major pathways. That here the nitrogen is attached to two aromatic rings, right?
Yeah.
So parahydroxylation can take place either on this ring, like this one, or on that ring, like right.
Sorry.
Okay.
One second. It's okay. Sorry.
Okay. If you want to answer, no problem.
No, it's my roommate.
Okay. So actually, this ring can undergo further metabolism after this and would undergo the second para hydroxylation to have the OH in the para position on both rings.
And
Okay.
the para is more common than the ortho because of the steric clash.
Static clashes, yes.
Okay.
Okay.
Yeah.
So here examples for the aryl propionic acid. We have the ibuprofen. We talked about it and we said the S enantiomer is the active form. We talked about its metabolism. Also the ketoprofen and the phenoprofen, we talked about also the metabolism. The ketoprofen can undergo oxidation or reduction. The phenoprofen only oxidation. Is it clear?
Yeah.
Okay, you have other examples, but if you looked at them, they are having the same star, aromatic ring, the naproxen, CCOH, and a methyl on the carbon. Also here, aromatic ring, CCOH, and methyl on the carbon, and so on.
Yeah.
Okay. Shall we go to the other class? Do you have any problem till now? Till now, we said the salicylates class, right?
Yeah.
The aryl alkanoic acid derivatives, which is divided either to aryl acetic acid derivatives or aryl. Okay,
Yeah.
okay. Other class here we have aryl antranilic acid. Okay, the anaryl antranilic acid, or what we call them the phenamates. Okay, so phenamates or aryl antranilic acid, both of them are the same. What do we have here? Here we say that they are bioisosteres of salicylates. Why? Because here the salicylates is COOH, and in the ortho position we have OH, right?
Yeah.
Here instead in the ortho position OH we have an H. That's why we call that the phenamates are bioisosteres to the salicylates. Okay? Again, this N should be ortho to the COH.
Okay.
And again, this nitrogen is going to be attached to another aromatic ring. This aromatic ring would have substituents on it. Substituents on this other aromatic ring in the ortho and the meta positions increases the activity. Okay?
Yeah.
However, this ring, the antranilic acid ring, should not have any substituent on it. Any substituent on this benzene ring of the antranilic acid would decrease the activity. Okay? This nitrogen should remain nitrogen. If we are having oxygen, sulfur, or carbon, again, the activity will decrease. Okay? Is it clear?
Yeah, so the no substituent on the benzene ring because it will decrease the activity, and it has to
On
be
this ring,
nitrogen.
the one on the antranilic acid, but the other phenyl ring, no. The substituents in the ortho and the meta increases the activity actually because, again, it will increase the non-coplanarity.
Okay.
Okay?
Yeah.
Is it clear?
Yeah.
So here for the phenamates, it's very easy. Bioisosteer for the salicylates, this nitrogen should be kept nitrogen. Any replacement will decrease the activity. This ring substituent on the ortho and the meta increases the non-coplanarity, increases the activity. And again, the nitrogen should be also to the carboxylic acid groups.
Okay.
Okay? We have the mefenamic acid, and here we have the tolfenamic acid. Okay?
Yeah.
Okay. Do you have any problem? Because by this we are done with the aryl antanylic acid, the phenamates.
Okay, so the important part is it has to be para substituent to the nitrogen. It has to be nitrogen. There has to be no substituents on the antarylic acid chain or region, and
Yes,
substituents on the other substitute or on the other benzene ring. It's okay because it increases the coplanarity.
the non-coplanarity.
Yeah, non-coplanarity. Sorry.
It needs to be non-coplanar, okay? Again, this part in your slides here, I'm having here the N-antranilic acid. We said they are bioisosteres of salicylic acid. Replacement of this nitrogen would decrease the activity as we've said, okay? For the metabolism of the mefenamic acid, you will find it very easy. Again, the COH can undergo glucuronic acid conjugation, as we said, okay? Here, it's telling you that this carbon, it's attached to benzene ring. This is benzylic. So it would undergo benzylic oxidation, becoming an alcohol, further oxidation to give me acid. And again, whenever you have COOH, they can undergo glucuronic acid conjugation. Is that clear? The other example, again, the meclophenamate, having here two chlorines in the ortho position and in the meta-methyl group. Again, benzylic oxidation takes place to give me CH2OH alcohol. Further oxidation would give me carboxylic acid group. Okay?
Yeah, and if it makes
Another
if it makes the toxic phenolic amine, we use the
exact.
same metabolism as we did
Again,
before.
here we are having what? We are having nitrogen attached to aromatic ring, to benzene ring.
Yeah.
Like the diclofenic, you can write it down. The diclofenic was exactly the same. It's having a nitrogen attached to benzene ring. So here para oxidation can take place, and then this ring can undergo further oxidation to give me the quinonimine, which is toxic.
Yeah.
Is it clear?
Yeah.
Sure, I think it's easier now.
Yeah.
Okay, you're welcome. So by this, the N-aryl antranilic acid, we are done with it also. Let's go back here. Yes, here, this class. This class is called derivatives of para-aminophenol or derivatives of aniline.
Yeah, it's paracetamol.
Yes, exactly, the paracetamol, the acetaminophen. This is the acetaminophen, and the other name for it is the paracetamol. Okay? What can we do here, or what is our problem here? If you can see here, we are having NHCOCH3, and again here OH, right?
Yeah.
NH, benzene ring OH, so this drug can undergo metabolism to give me something similar to the quinonimine,
Yeah.
which we call here the NAPK. This again is hepatotoxic. It can react with hepatic proteins causing toxicity or glutathione which make detoxification, or at high doses we can give antidote. Here it's written here, the N-acetyl cysteine. Okay. Okay. Here the we have other drug, but actually it's not a well-known drug called the phenestin. Okay. Actually, this is having here, it's similar to acetaminophen, but instead of OH, we made OCH, sorry, OC2H4. We made an ether. This group inside our body would undergo metabolism or dealkylation to give the acetaminophen and go the same.
So phenacetin is a prodrug.
It can be as a prodrug, yes, we
Yeah.
can, but it's not written like this in your slides.
Yeah.
Okay. Okay. Here again, we having without this OH, we are having something called the acetanilide. This acetanilide can undergo metabolism, removing this acetyl group. Deacetylation takes place to give me the aniline ring. This is aniline ring, right?
Yeah.
This aniline ring causes something called methemoglobinemia. Can you remember what is the difference between the hemoglobin and the methemoglobin?
Yeah. The iron changes to the F3. It moves to
Exactly.
F2, and it cannot
Yeah.
it binds to the
Cannot carry the oxygen.
hemoglobin. Sorry.
Yes. It cannot carry the oxygen efficiently to
Yeah.
the tissue.
Yeah.
Exactly. So that's what the aniline would do. It causes oxidation to the iron from ferrous to ferric, causing methemoglobinemia.
Yeah.
Okay. Is it clear?
Yeah. And it's not a true NSAID because of like the anti-inflammatory.
Yes, exactly. Is it clear?
Yeah.
Actually, this was mentioned here. We went through all the slides, by the way. Okay. It was at the beginning, I think, one slide. Yes, here. It was the first thing in the classification. Derivatives of aniline, they call it aniline. This is aniline, or para-aminophenol, which is NH2, and here it's going to be OH. Okay.
Yeah.
This is the metabolism of the acetaminophen mainly, which is the paracetamol. And they say that the acetaminophen, it causes hepatic necrosis. It's hepatotoxic, as we said before. Okay. And again, it states that it interferes with enzymes involved in the coagulation pathway. Do you have any problem?
No.
Okay, we are almost done. We have only one class here, the oxycam. Yes, the oxycam here.
Yeah.
No, the oxycam, they are not cool. They are still
The selective.
yes, this is the last class on the non-steroidal anti-inflammatory drugs, non-selective. Here, the oxycam, this is structure for it, okay? And what is very important, uh, the oxycam, here is the structure, okay? This is the structure of the oxycam. What is very, very important for me in this part is that the oxycam is the only one throughout all the drugs that we have mentioned that it's not having COH. Do you have here COH?
Yeah. We don't.
We said that all of them are having acidic, they should have acidic center, right?
Yeah.
Okay. Here, the acidic center, if you are asked, is not the carboxylic acid group. It is this, the enolic acid. Okay. This H in the OH, this is acidic. It can be lost and give H plus. Why do we call it enol? Enol means C double bond C OH.
Okay.
Enolic acid because here it is attached also to this amide group, to this C double bond O.
Okay.
So if it is drawn and I'm asked you where is the acidic center here, this is the enolic acid is the acidic center here. Okay?
Yeah.
Okay, great. This oxycam is having something called the benzothiazine. What is benzothiazine? I have a benzene ring, and this is thiazine. Thiazine means six-membered ring. Thi means sulfur, as means nitrogen.
Okay.
And here on the sulfur, we have two double bond O. So that's why we call dioxide. You will find in the name 1,1 dioxide. At position 1, this is position 1. 1,1 dioxide. Okay. Okay. And here, this is one, two, three. At position three, we are having what we call the carboxamide group. The presence of this CH3 group and this ring is very important. It enhances the potency and increases the activity. Is it clear?
Yeah, probably then also increases the non-coplanarity.
Yes, exactly. Example for the oxycam, we have the meloxicam. This is the meloxicam having the benzothioxine ring. This is the acidic OH. And we have here the aryl group attached to the carboxamide is essential with this CH3 to cause the non-coplanarity and make the activity. What is the metabolism here? This CH3 attached to aromatic ring, so it would act as if it is a benzylic carbon and it would undergo oxidation to give me the alcohol. Further oxidation gives me acid.
Yeah,
Is it clear?
yeah,
Okay. This is the only thing that you are having. You have here the structure and the metabolism of the meloxicam.
yeah.
Okay, is it clear? I think we are done. I will tell you very quickly the selective COX-2 inhibitors. You don't have a lot to talk about. Actually, all of them, or most of them, 99%, they end with coxib. Okay? Or so, coxib, celecoxib, rofecoxib, and so on. These structures are mainly having sulfonamide as the acidic center. They are also, most of them are not having COH. You will find they are having either this sulfonamide or the sulfone group here.
Okay.
Okay?
Yeah,
Is it clear for you?
yeah,
Okay. So here we are having the sulfonamide, here sulfone, sulfonamide, sulfonamide, sulfone, and only the lumiracoxib is having the carboxylic acid group. For the metabolism of the salicoxib, again, this CH3 attached to the benzene ring, so benzylic oxidation takes place, followed by further oxidation to give me the acid, and it's telling you that this acid would undergo further oxidation to give glucuronic acid conjugation.
okay.
The acidic part is the sulfonamide, as we said.
Yeah,
Okay. Yes, actually, COX-2 inhibitors, they are mainly used in the rheumatoid arthritis and osteoarthritis, and they are having side effect, cardiovascular side effects. Okay. The COX-2 decrease the GIT side effects. They do not have GIT side effects. However, they have side effects on the heart, on other areas. Okay.
yeah.
Is it clear? Okay, we are done with the non-steroidal anti-inflammatory drugs. Do you have any problem?
No, everything sounds clear.
Okay, welcome. Just study, and I hope you the best in your exam. I don't know if you would need any further revision. By the way, I'm done with I don't know with the H1 antihistaminic if you need to take it. I don't know.
I will just take the first part and now on Tuesday, and then and then I will take the rest in September. But if I need help with any other topic, I will let you know maybe by the end of today once I decide, or maybe tomorrow morning.
Oh,
So you have a bit of time to prepare, and but I'll let you know. There's a possibility one more class if you'll have time over the weekend.
okay, just let me know because actually my weekend is today and tomorrow.
Ah, okay, okay, okay,
So just let me know when would you need and which topic, and we can manage it.
okay. Sure. I'll let you know easily. Thank you so much.
This topic now is very easy. The opioids, I think it's